Hello everyone, my project is evaluate Webrtc on the real world. Uh, what is Webrtc? Webrtc is an open source project that allows web browsers and applications to exchange real-time audio, video, and data directly without requiring plugins or dedicated software. So, why I choose the WebRTC for my project? I answer to the next. Why I choose WebRTC for my project? After the pandemic, the use of WebRTC significantly increased due to the rising demand for reliable remote communication technologies, making it an essential choice to future. I choose Webrtc because it provides powerful real-time communication, uh, ideally suited for real-time applications such as media entertainment, live video monitoring, video conferencing, and telehealth. That the use of WebRTC significantly increases due to the rising demand for reliable remote communication technology. So, uh, during this presentation, first I talk about the type of servers that WebRTC use it, and then what is the media server, and I talk about the feature my test bed that I used in the project, and then show the demo and some result that especially I choose because of the lack of time. I couldn't show all results of my project. WebRTC signaling is how browser agrees to connect before exchanging media. A signaling server helps peers discover each other, negotiating parameters, research, or close connection, but doesn't carry the audio or video itself. Because NAT routers hide local IPs, peers can't always advertise reachable addresses. To fix this, WebRTC use ICE candidates that includes the local peers and the remote peers. Eastern is the client asks a public Stern server, what's my IP, and uses that it in its session description. Turns is the server that if the stun fails, uh, because of the strict NAT, media is relayed through a public turn server, bypassing the firewall entirely. What is the media topology that maybe WebRTC use it? There is, you can see three topology. First, mesh. Every participant send their audio or video directly to each other. Second, MSU, a central multi-point several unit receives all streams, decode, mix, and re-recoded them into one composite stream per user. And FSU simply forwarded each incoming stream to all other participants without mixing. That Google Meet use FSU for their connection. So I want to show you the demo that how I work during my project. My testbed setup includes some laptops and a smartphone. And the software that I use is the Google Chrome that I run the Google Meet on it, and OBS Studio for fitting a fake video for a camera, and Python to run some script. And then I use the WebRTC internal for a dump file, and my networks is LAN, Wi-Fi, LTE, and Starlink that I examine the WebRTC during the Google Meet on it. During my project, first I establish meetings between users in the special scenario, and then collect the log file with the dump WebRTC file, and then I use the special script to analyze and visualization of the results. First, I open this API to collect the DOM file. You can see in this part after the call, I download the WebRTC internal DOM. And then I open the OBS Studio to feed my webcam, start virtual camera to feed the camera with the special videos. So I start meetings. You can see can shows the special video with the OBS virtual camera. I join it. So another user start to join. Yeah, and then after the the meetings, uh, I run a special script that writing the Python that helped me to visualize the result. So at the result, you can see these multiple panels show the result that I collected during a special uh, scenario between two Wi-Fi nodes. This multiple panel chart shows 7 key WebRTC metric over time. The top two panels track video resolution that you can see the average of it, and the third panel shows the frames decoded per second, averaging 29.65 per second frame per second. So a smooth 13 FPS playback with only a couple of momentary dips. The fourth panel is jitter that which stays near 0 millisecond, expect for two small spikes. At the bottom three panel plots show the round triple time for outbound RTP for inbound and IC candidate pair, all averaging on under that uh, 0.1 second, means that 100 millisecond, and the so after you can see that the special spike exit on it, but after they come back to the normal condition that demonstrating seamless adaptation and ultra low latency performance. So after This script show me the statistics information about the scenario, for example, jitter, RTT, frame per second, frame decoded per second, and other things. Okay, my project includes the more results and more plots. Just I want, because of the lack of time, I show you the some special part of the project. Uh, I want to show you the some samples and the result about the IC candidate, and then show you the some scenarios. Uh, I evaluate five scenarios in this presentation. I show you all appears on Wi-Fi, on wireline, on Starlink, and on a cellular network. And the case where peer switch networks from Starlink to Wi-Fi and LAN to Wi-Fi, so we can compare Webrtc across these uh, different link types. Uh, what is the ICE candidate? ICE candidate has all the possible addresses your browser can use as your local LAN addresses, the public IP or STAN services, and a relay on a turn server. The browser collect all these addresses collected, and based on the special algorithm calculate the special priority and select peers as a local candidate and remote candidate. And IC then picks this fastest and reliable pair at the ICE candidate. In this scenario, you can see the ICE candidate start checking on the 11:23:31 second and establish and connected in after 1 second. And the average RTT between this candidate is around 40 millisecond, and you can see the local and remote candidate use the IP version 6, and the type of protocol is the host, and uh, they use UDP for the connect. In the LTE scenario, both peers are on the cellular network connecting through Google Meets server. On the right, Webrtc internal shows IC moving from the checking to connected within the same time step, indicate NAT traversal complete in under a second. The local candidate is a peer reflexive UDP address, uh, and this address is for maybe NAT, and this address is uh, for the remote local. So for the in the Wi-Fi scenario, both laptop connected with the wireless LAN, and you can see the WebRTC internal show that the IC going from the checking at 15.8 second to connected at 15.9, and around 1 second they need to negotiate it, and they use the UDP, and both of them all host, and this is my IP, and this is the remote candidate. For LAN scenario, you can see that the both laptops sit behind the same router and the wire connection during the Google Meet on the right side, and you can see IC go to checking at 32 seconds to connected at 34. Just they need 2 seconds for handshake because use the TCP and both and the both is behind the net and use the uh, uh, um, prefix uh, types, and the average RTT between two peers are 11 millisecond. And you can see the type of the connection, and the type may be host when they the machine have a own IP, and with own IP make a connection with the remote uh, server reflecting uh, they gain the IP after they related with the start and prefix a new address. Learn when your peer reply on the IP or port you didn't originally gather. Often a NAT remap on your peer side relay is a combination of IP and port on the turn servers. So, in just in this slide, you can see some statistical about my project. LAN delivers the best media quality over 1300 kilobits per second of outbanded video, under 3 milliseconds of jitter, and zero packet loss. Wi-Fi comes next with about 913 kilobit per second video, 9 millisecond jitter, and essentially no loss. Starlink sits in the middle, roughly 515 kilobits per second, near to 15 until 90 millisecond jitter, and tiny 0.1% loss on audio and video. LTE showed constraint only 140 kilobits per second video, but it boosts audio in the 14.8 kilobit per second with 20 until 30 millisecond jitters and no loss. In short, WireLAN is ideal. Wi-Fi is solid for Moscow. Starlink is usable, but uh, has higher delay and a slight loss, and LTE work but severely limited video quality. In this test, we switch mid-call from Starlink to Wi-Fi. ICE ICE initially checked at 13.1 and connect 1 second later with very stable stat near zero packet loss and jitter around 15 to 20 millisecond, and RTT about 14 millisecond. At 11, 13, 20 second, we physically move up Starlink onto the Wi-Fi. IC report disconnected and then immediately connected. You can see a burst of packet loss in the flight packet drops, and one IC renegotiate over the Wi-Fi link. Performance quickly established, packet loss return to zero, jitter allow to return to jitter falls below the 10 millisecond, and RTT settle around 15 millis, showing seamless failover with only a brief disruption. Uh, Here we start on another scenario. Uh, switch from LAN to Wi-Fi, IC began checking at the uh, f- uh, 10 second and connected by 14:34:11. Jitters is sit under the 10 millisecond RTT uh, around 10 millisecond, and a packet lost and no packet lost. At the 6 second, we unplug in the LAN and switch to the Wi-Fi. IC shows disconnected and then connected, and you can see just 1 second, and we see that the packet lost, and then uh, Wi-Fi performance is stable. Jitters falls to the 20 millisecond, RTT to 20 millisecond, and packet loss return to 0. Demonstrate a subsequent failover with only a brief, quickly dip. Future work, I suggest three area: optimize IC candidate selection, especially for stalling, and refine the IC candidate selection formula, and refine media topology to gain a better performance and reduce the lag. Thanks all. If you have any question, ask me. Thanks.